3.6 derivatives as rates of change. So in this section, we want to use rates of change, meaning things like in the real world applications as like the usage of the internet growth. We could do blood pressure as it changes. The universe's expansion is another good example of rates of change. And that's why calculus is definitely called the mathematics of change. So in this section, we're talking about derivatives as that rates of change. We've kind of already talked about it, but we're going to come back to it for a little bit. So position and velocity, remember, suppose an object moves along a straight line, its location in time, time is always going to be the independent variable given by the position function s equals f of t. This book does like to use f of t instead of s of t for position. So we are used to s of t. I will try to always rewrite the position function with s of t. All right, remember what displacement is. Displacement of an object between some time and where we went at the end of some change in time is basically the differences in our y values. So the displacement is this, which is a big key fact. Where did we end up as far as the distance change? Is displacement. We have the definition for the average and instantaneous velocity. Let s be the position function again. The average velocity is the slopes over an interval where we started at some value of a and like where from a some time later that we changed did we end up. It's the secant line slope between these 2 points. So we could have the average velocity is equal to the delta s over delta t, which is in a sense the same thing as the slope. Remember then, instantaneous velocity at a certain point is when we take the limit of this slope and we're trying to get this limit so we can approach zero, have it be that actual value of a we can use, and then find the derivative, f of a, really being the velocity of a. So instantaneous, at that instant, what is happening? What is the slope of the tangent line? Remember, why do we want to know that? That gives us, the tangent line gives us the direction for a trajectory of a velocity. So note the various derivative notations we can use when writing the velocity. They have the v of t, which is the derivative of the position function. And they said it's also, we can write it as ds over dt for velocity, instantaneous. Remember, if it does not say average or instantaneous, if it just says what's the velocity, we're going to understand it to be instantaneous. All right, so I have an example. This is number 8 in the book, page 187, and they have a better graph than I do because I drew mine. And we have this graph. Obviously, it looks some kind of like bell curve, but it kind of does. It's supposed to look like it flattens out for a period here. So let's go ahead and see what the book says is the problem. Number 8 in our textbook says, the following figure shows the position function of an airliner on an out and back trip. So going there and coming back from Seattle to Minneapolis, where the position function is the number of ground miles from Seattle in T hours after takeoff at 6 a.m. The plane returns to Seattle 8.5 hours later at 2:30 p.m. A wants us to calculate the average velocity of the airliner during the first hour and a half of the trip. So they want us to go ahead and calculate from t being from starting at 0 to 1.5. So we're going to go ahead and just assume we are going to use average velocity, or this point, to start. And at 1.5, it looks like I have an output of maybe 600. So I have 2 points, 0, 0, and 1.5, 600. We can calculate slope from here. It's the average velocity, so it'll be 600 minus 0, all over 1.5 minus 0. We end up with 400, should be miles per hour. This is part A. Part B wants us to figure out the average velocity from 130 to 230, or from our t interval 7.5 to 8.5. So we're going to use 7.5, excuse me, to 8.5. And we can see on our graph that from 7.5 here, it looks like maybe we're 400, and at 8.5, it looks like we're at the point 8.50. So we can use those 2 points. And we can find slope, average velocity. Oh, did I say 400? Should be 300. Sorry, guys. 300. Or a negative 300 miles per hour. Now remember what we're talking about. Why is it a negative velocity? So remember what this graph is. This is where we're saying the plane took off, and obviously remember we kind of had that flat area, and then the plane came back to the starting point. So we went from one point to another and came back. So that we actually are saying, as far as position, if I did it on a number line type situation, we can call this Seattle and this Minneapolis. And it looks like from our graph of this interpretation, we should have reached our destination, Minneapolis, at 3 hours. Or, remember, we left at 6 a.m., 9 o'clock. So it looks like what we did is the plane took off, it flew here, we were stuck there somehow, so we stayed there for a while, and then after we came back to the same destination. So if this is the case, this last period of time they wanted us to look at from here to here would have been a negative velocity. Makes sense. It also looks like from our graph a negative slope. So then we're going to go ahead and do part C. It said, at what interval does it appear the velocity is 0? Give a plausible explanation. Well, remember, when the slope is 0, or when the velocity is going to be equal to 0, is when we have a horizontal tangent. And it looks like an interval of time from our chart from here to here. It means the plane wasn't moving. It looks like from hour 3 to hour 5. So it looks like, if we put it in time-wise, it looks like from 9 o'clock to 11 o'clock, the plane was at rest. The book says in part D, we want to know, determine the velocity of the airliner at noon when t was 6 and explain why the velocity is negative. Okay, so we want to know when t equals 6. That's noon. And if we go back to our graph, when t equals 6, it looks like our output or position was at 1200, and our velocity, which is the tangent line at that point, is negative. So it said, why would it be negative? That's because it makes sense. We're on the return trip. So our velocity would be negative at that point. So when we talk about velocity, speed, and acceleration, we want to talk about what is speed and acceleration. Remember, like I said, if we had some particle moving in some path, it tells us the tangent line at a certain point what the trajectory path is at that point. That's the equation of the tangent line. And from there, velocity has magnitude and direction. It's a vector. So if I want to talk about speed, speed has to be the absolute value at that time because speed is magnitude of the velocity. Speed does not have a direction, so it's absolute value of it. And then we're talking about acceleration. Acceleration is a rate of change of the velocity. Rate of change of the velocity means we take the derivative again. So we always think of it as rate of change of velocity. So that's why our notation here is where the acceleration is going to be dv dt or d squared or d double prime, not squared, double prime of the position function. So we have that. And then remember, acceleration could be positive or negative, increasing or decreasing. Remember, it's possible for speed to increase while velocity decreases. That's a concept sometimes hard to understand. But let's go ahead and try to work with problem number 10 in our textbook. So for problem number 10, it gives us this function and its position function. So I'm going to call it s of t as negative t squared plus 4t minus 3. On this interval of time from 0 to 5. So the first part of the book says, okay, graph. Let's graph this picture roughly. We're only going to be doing not this part of the graph. Remember, we're only going from 0 to 5. My graph does roughly look like this. And it has that shape, a downward parabola, quadratic. All right, so this is its position function, s of t. B wants us to find velocity, meaning v of t. I'm going to go ahead and take the derivative of the position function. And I get negative 2t plus 4. And then the book says, okay, for this one, if we find this velocity, graph that also. So I'll use the same graph, but I'm going to put velocity in red. And I would have to graph this linear equation. This is my velocity. Remember, this one was my position function. All right. And wait a minute, I goofed up because we're not going past 0. We're starting from 0 to 5. So I'm going to stop here at 5. All right. Then it says, where is this moving right, left, and where is it stationary? When we're looking at this picture of the velocity, we want to remember in a velocity graph, positive slopes, negative slopes, and at rest is when m equals 0. So we're resting at some point in between. So from this example, because of the red line, I do have from 0 to 2, I'm moving right because I'm positive. And then when t equals 2, I'm at rest. And then from 2 to 5, I'm moving left because I'm a negative slope. All right, next in our book, we want to know what is the velocity and acceleration at 1 when t equals 1. At 1, in this case, is it 1 second that we want to know? They didn't tell us a unit, but whatever unit of measurement for time, we want to know what the velocity would be and the acceleration would be. Well, we already have the equation for velocity, so it would be -2, plugging in my 1, plus 4, or my answer is 2 feet per second. Then acceleration, if I want to evaluate that, I have to find the equation. So in order to find the equation of the acceleration, remember it is the derivative of velocity. So taking the equation -2t plus 4 and taking its derivative would be -2. So it doesn't really matter that I had to plug in when t equals 1. This is a constant acceleration here. It's 2 feet per second squared is our acceleration. Part D of this problem, they want to know the acceleration at 2 seconds. Well, and that's the case. Remember, we found it and it's a constant. It's going to be -2 feet per second squared. I want to talk about free fall. When we're talking about free fall, in these cases, we're going to talk about gravity only as a factor on this acceleration velocity of something falling. We're not going to talk about wind resistance or anything. We're only going to talk about gravity. So the acceleration due to Earth's gravitational field is denoted G in metrics, and we're going to use these two units of measurements, so the U.S. customary system and the metric system. So I want to do example 22 from the homework. And they give to us on number 22 that when we're comparing velocities of two stones thrown vertically upward with a matching velocity of 48 feet per second at time equals 0. So they are going to be launched same path, with the same velocity, initial velocity, and it says one stone is thrown from the edge of a bridge that is 32 feet above the ground, and the other stone is thrown from the ground. The height of the stone thrown from the bridge after t seconds is, and they're going to give us the position function for the first one. This is going to be for the bridge, and its position position function is -16t squared plus 48t, because that's our initial velocity, plus the height of 32 feet. The second one from the ground is given this position function, that it's -16t squared plus 48t as an initial velocity. So from here, they want to know in the book, show that the stones reach their high points at the same time. So how do I show that? Well, in the way, I'm really going to look at when velocity is at rest. Because if they reach their high points, if they're going to follow a typical trajectory path, when it's at rest, that's its highest point. So both of them, if we're going to prove they're the same, should have the same time of where the velocity is equal to 0 at rest. So I'm going to take the position function and find velocity. And from that one, I get -32t plus 48. And if I do the second equation, I get -32t plus 48. It ends up being the same. I can already see from here, it's the exact same equation. If I set each of these equal to 0 to find when it's at rest, they should be the same, and I should get t equals 32. So at 1.2 seconds, they're the same, and they've reached their max height. So we've proved that. Then in this book, it says for B, how much higher does the stone thrown from the bridge go than the stone thrown from the ground? Well, if we actually look at our initial position functions, what is the only difference between the two is this initial height. It's that only thing that was added on to the equation was that 32 feet from the bridge. So our answer for B will be 32 feet. All right, from here then, it's C. It says, when does the stone strike the ground and with what velocities? So what I need to do is set each of these equations, the position functions, set them equal to 0, and we'll get two values for this parabola where they cross x-axis. And these are going to be where we're going to be hitting the ground. Now it makes sense, either one, that we're assuming we're going from the ground and from the height of the bridge, we're going to disregard the first values we get. We're looking for this second point of when we're going to come back and down and hit the ground. So you can find those, and then from there you can plug that in, whatever value you find when it was equal to 0, we're going to plug that into the velocity equation to get at what velocity it's striking the ground. We have then, we want to talk about average rate of growth. I don't walk through any of the homework examples that I like for this one, but we're talking about average growth rate. Everything is still the same, just other than the little bit of the notation. They're saying let P equals f of t for the growth rate. All right, so instantaneous growth rate or simply growth rate with respect to time. If you look in your book on page 186, example 4, and walk through that, they use a bunch of data points, and I want to point out that I don't think is clearly explained in the book, that they're using basically a scatter plot. And then they're saying, well, graph this. You're going to want to use a quadratic regression. And in a sense, they actually give it to you. They give you a position function they're calling P of t in the book. So for step A, it's talking about slope over an interval, so you can use slope. B, we go ahead and take the derivative of the function for some A value. C, they graph this derivative. And then part D, they are using the equation as a prediction equation. So they went ahead and they're saying, well, for some value in the future, they just went ahead and substituted it right into the equation and evaluated using prediction properties for that.